Hello, welcome to this video. Now in this video, I'm going to talk about something which very few people talk about, and that is the IoT architectures. Far many experts, far many academicians and many industrial people also many a times take IoT in a completely different direction, or they can think of IoT as something very simpler, or they don't see the full picture of IoT. So in this video, we're just going to demystify that. We are going to see everything that IoT can be, IoT can encompass, and IoT that can do. So let's get started with understanding the IoT architectures in full. Now to start with, I have a very simple 4-stage reference architecture for IoT systems. Now it doesn't matter which IoT systems you are creating, if you are connecting 500 buildings spread across the world, or if you are simply building a small plant watering system, it will be captured by this reference architecture. What normally happens is anyone who is starting to experiment into IoT looks at the primary tutorial video where something like a Raspberry Pi Pico or an ESP32 or any such Wi-Fi enabled microcontroller or Raspberry Pi is connected with a sensor. That sensor sends data, or the Raspberry Pi or that Arduino or that ESP32 reads the data from sensor, sends it directly to a cloud service where a readily available dashboard is there. You can see this value on these dashboards. If you make or click some buttons on this dashboard, then you can control the devices on your ESP32 or Raspberry Pi, and end of the story. It is a very valid, it is a very practical IoT application, but IoT is not all about this. It's never been, okay? So this is the 4-stage reference architecture that I'm going to talk about, and we'll see how it can be mixed and matched to match the specific requirement which I just explained. The very first thing, or the very first stage of this reference architecture, is the actual physical end of the system, the sensors and the associated embedded systems. Now the sensors and embedded systems, this is just a reference here, okay? It can be anything. It can be, if you are doing a simpler home automation system, then it can be temperature sensor, humidity sensor, motion detector. It can be a relay. It can be a plant watering system or a DC water pump connected to a relay. It can be any actuator and sensor. Anything that needs an action to be done in real world. Now, every such device or every such sensor or every such actuator cannot operate on its own. So it almost always requires some form of embedded systems connected to it. Now what is those embedded systems? This embedded system is nothing but typically a microcontroller which can have or which can communicate with the sensors and which can also activate the connected actuators. In an industrial environment, this can be a smart sensor which can directly send data to Wi-Fi or through different communication protocols. It changes from case to case, but normally speaking, the stage 1 can be considered as the first thing, that is the physical sensing part or the physical control part of this architecture. The second stage of this architecture is connectivity and gateway. Now, how we do that, how we collect the information using an embedded system or using any industrial readily available sensor or a smart device, whatever it can be. It can be a PLC system as well which has some sensors connected to it and it is reading information. Everything will come into stage 1. Stage 2 is connectivity and gateway. Now what does connectivity and gateway means? This is basically where the internet connectivity comes into picture, but at the same time something like an edge gateway comes into picture. Now many hobbyists and academicians who have been learning IoT from multiple sources, who have been learning IoT but not implementing industrial projects, they seldom know about this stage. What is this stage? What is this edge gateway? It's basically another small or big processing unit which sits between the internet and the sensors and embedded systems. Why it is placed there? There are multiple reasons for it. Consider a situation where you are reading information not from one sensor or not from one sensor node. For example, let's say it's an industrial system. Let's say there are 50 plus different machines operating in an industrial situation or a factory, and every machine has one sensor node connected like this. And every sensor node is reading at least 5 different values. Now imagine 5 values on one node and there are 50 such machines installed. So there are at least 250 different sensor values which are being sensed in that one factory environment. Now, instead of sending all those 250 sensors every second or every 5 seconds or every 10 seconds over to cloud, what is preferred is keep an edge gateway, keep a local gateway which sits within the same environment, which can read from all such nodes, which can structure that data, which can pre-process that data, which can also take any local action as and when needed, and then only send the important pieces of that information over to internet and over to cloud. Now I am simplifying this the purpose of edge gateway, but this is a classic example. Edge gateway can serve a number of different purposes. I'm talking about 250 sensor values. If you are in a smart building environment where you have HVAC controllers, you have building management systems, then there are at least 300, 400 different parameters coming in only from one building. In such situation, edge gateway is not just an option, but it is the only option to process such heavy information locally. Next stage that comes in an IoT architecture is the data and cloud. This is when the information is transmitted over internet. So this is where the internet will come into picture at this arrow, and when the information enters into the cloud domain. Now this is, many people, even hobbyists, are familiar with this. Whenever we are using something like ThinkSpeak or whenever we are using something like Adafruit IO, what we are doing is we are using one instance or one way of this particular stage 3 as well as stage 4. You can say combination of this. Now what the stage 3 basically means is, when this information enters into a cloud-based server, how do we accept it? How do we store it? Again, as I was saying, if you have always been using readily available platforms like ThinkSpeak or Adafruit IO or Blink or many such applications, then you are never aware of this particular configuration. That's where becoming a professional IoT system engineer or a professional system designer and hobbyists will differentiate you. Because in many of the installations, in many of the product development situations, you will not be using something like Adafruit IO or ThinkSpeak. ThinkSpeak maybe, but in most cases, we need to properly configure our cloud platform so that we can save the information coming in into a database. Storing this database is the prime important thing. And this stage deals with this cloud platform configuration and storing into database. Now again, in stage 3, you can have or create multiple different configurations. Almost every cloud provider like Microsoft Azure, AWS, Google Cloud, they provide their own managed IoT services where you can directly have an MQTT broker and some streaming service which can directly push that data into a cloud-based database. This is an option. Another option is classic one where you can create virtual machines on cloud, you can install your MQTT broker on those clouds, you can configure your own database on those clouds and then create whole system on your own. Why and how and which option to choose, it completely depends on the decision framework, which we'll discuss later. So this is stage 3. Stage 4 is once the data is saved onto a database. Stage 4 is all about visualizing that data through an application or a dashboard, creating alerts, sending emails or sending alerts back to these embedded systems to perform some actions and visualizing that data. All of that comes into this stage 4. Now if you think about it, if you take a step back and if you try to think of any IoT application that comes to your mind, it will always follow at least 2 or all of these reference architecture stages. Think about it. Now, the next thing I want to talk about is the decision framework. Now, what is the decision framework? Okay, let's say we are creating a complete industrial IoT system where we want to do all four of them. So there would be a lot of decision that needs to be made at a lot of different points. Which microcontrollers should we use? Which kind of sensors should we use? How these microcontrollers or how these sensors, or if we are using ready-made sensors which can directly transmit data, then how do they send information to this gateway? Do we want a wired communication channel here, wireless communication channel here? We want to use Wi-Fi here, or any other RF protocol or any industrial protocol? How these devices should operate? Should they be operated on battery? Should they be operated on external power? A lot of different things in just the communication from storage to connectivity. Then when it comes to connectivity or gateway, if you have decided that you have to create a gateway, then should we create a gateway out of Raspberry Pi? Should we create a gateway out of a general purpose Linux computer? Or should we directly go for an industrial grade IoT gateways that are available in market? Those choices will be here. Again, how do you process the information on gauge? The selection of software on this stage will also be into picture. So on and so on. There will be number of such decisions you will have to make around device hardware and software, connectivity, and the cloud platform and services. And most of the times these decisions are governed by these factors: business requirement, how much data, how much and how tight you want the security to be, how much is the cost impact. If you are creating an end product, a consumer product, you need to be having the minimum cost, or it should be the lowest priced device that you can create. If you are creating an industrial IoT system where the security and robustness of the system is prime importance, then cost is not that sensitive. How much do you want to scale it? As I said, if you are creating consumer electronics product, then it needs to scale to 50,000 devices or millions of devices, it doesn't matter. And how you want the overall user experience to be. Again, if it is an industrial system, you don't have to be very heavily focused on user experience. But if it is a consumer electronics device, then the UX needs to be extremely pleasant. Otherwise, the users will not adopt to your system. So, it doesn't matter which system you are creating, it will always be falling under these architecture frameworks and one or more of these decision frameworks. I am just putting 3 pillars here. There are multiple pillars that can come into picture when you are actually creating a system. Now, having said that, it's very easier for you now to understand what are the different mix and match configurations that are created, or what are the different architectures that are created out of it. The very first is, as we discussed, the full 4-stage architecture. Consider this happens only and mostly in typical complex large industrial IoT systems or building management systems or smart factories. In such situations, this kind of system is designed. Clear separation of duties, and you can create each system such that it is plug and play. The system should be created in such a way that if there are 10 different devices, then failure of one should not fail the system. Similarly, the stage 2 should be created with such redundancy, and so on and so forth. This is the full 4-stage IoT architecture which is used in industrial IoT. Now, what is most common is direct device to application. This is what, when you pick a microcontroller and send data to a readily available cloud SaaS service or IoT platform, this is what we are creating. It's basically simple, very easy to prototype as well as easy to manufacture, and it can push data directly to internet. The internet capability here mostly is Wi-Fi, many a times 4G or 5G, and there are multiple such communication protocols available as well. The classic example which many of us are actually using are smart plugs, which can control any particular appliance using a mobile app. Then there are simple learning projects that you can create, or early IoT systems, or basically prototyping system. Even if you are going for such a complex system, the prototyping can start with this architecture. Wearables and most consumer products, if you are purchasing an air conditioner which markets itself that you can turn it on before going home, then it is basically this direct device application, direct device to cloud and application architecture. Of course, the internet connectivity and the local internet gateway will come into picture, but it's not a smart device. It's not something that you have to build. So you just install that device, connect it to your Wi-Fi, and it connects to its own service provider. Smart lamps is one such example, and there are many such things you can think about it. The next and most commonly seen architecture is edge-heavy systems. Now, in edge-heavy systems, what is typically done is, instead of creating the whole bunch of processing, instead of creating a whole bunch of database and a very complex application on cloud, most of these things are handled locally onto the edge gateway. Why this is performed? Because two things. One is you reduce latency in the communication from gateway to cloud and cloud back to gateway. And second is you perform or you save extraordinary costs if you are going this way. Instead of hosting your database on cloud, instead of hosting the whole application on cloud, if you do all of those things on a gateway, then the pricing aspect reduces drastically. And in such cases, cloud is used only for monitoring purpose. A very small fraction of data would be sent over to a simple cloud application. It won't be complicated. It won't be as complex as the full-scale application. Normally, this is preferred by many of the industries who need local automation. This is also preferred in situations where connectivity is not that great, like forest area, coal mining area, or any kind of military area, where connectivity or security of the connection is a concern, and industrial safety systems as well, because safety systems cannot rely on some analytics that are being performed over cloud. The internet connectivity may go down anytime, and it happens in every place on this planet. It just happens. You cannot guarantee 100% internet uptime. So this is a preferred way of creating any complex system where security is a must. Then comes another system where many people, or this is mostly small manufacturers or places where data security is of utmost importance, they completely skip the internet part. Now, if you see a system like this, do not discard it saying it's not Internet of Things because where's internet? No, it's not the case. So this is also the IoT application where everything is performed in stage 2 only. Everything is done in the local gateway itself, including the dashboards, including the complete visualization applications, the alerts, the analytics, everything. Now, here the edge itself acts as cloud. If there are any kind of alerts or mechanisms or remote monitoring are needed, then this edge device may send SMSs, or they may use something like a WhatsApp bot or a Telegram bot, where they can send SMSs to the owner or the concerned people about any specific alerts. Apart from that, there is no processing required on cloud. Now, these are some of the examples of how the cloud architecture can be tweaked for your particular case. The most important thing is IoT architecture is not about tools, it's about the structure. In every stage of the architecture, or to design any stage of that architecture, you will always get number of different tools, and there will be number of different options in every stage. But as someone who needs to be an expert in IoT, you shouldn't be concerned, or you shouldn't become very much attached to the tools. Instead, you need to understand the structure. Tools are just tools. You can use them, you can replace them. If you are creating one system, you will be using Raspberry Pi Pico. If you are using another system, you will not use any embedded system at all. You may use complete industrial sensors which can send data over CAN bus. Then you will have an IoT gateway which receives data or information over CAN bus. All the sensors can be read on that IoT gateway completely on a web-based UI, and then that web-based UI will communicate with its own web-based UI somewhere on the cloud. Everything is IoT. All such systems are IoT. So my recommendation always is to all learners is, when it comes to IoT, think about the architecture. Don't think about specific tools, programming languages, or cloud. Again, gateways, as I said, are architectural choices. Gateway is not a requirement. If you are having a smart AC, you do not need a gateway. If you are creating your home light control system or your home automation system, you do not need a gateway. If you are creating a GPS based vehicle tracking system, you do not need a gateway. Okay. Every system that we create is a choice, is a trade-off between all the available options. This is never a standalone straightaway solution that if you have to build a temperature controller, you need a sensor, you need a relay, and you need a controller. That's it. No. Every requirement will define your architecture. However, the fact is the reference model never changes. This will always be there. Your options will change, your wireless wired connectivity will change, the way you create these applications, the kind of database you choose, the kind of cloud you choose will change. But in general, this 4-stage reference architecture will not change. I hope this was informative to you. Thanks for watching.